Welcome to the next version of our podcast. This is episode 21. It's been a while since we've recorded. It's been a quarter, so we wanted to get back at it and continue to speak about topics in AI that are of interest. So today I wanted to talk more about control theory and the dynamics and talk about LLMs a little bit and how all this kind of fits together and kind of share our viewpoints, and hopefully as always is helpful. If you're returning to listen again, thank you very much. If you're new, welcome, and hopefully you find this of interest. So let me start first with just a simple diagram. Typically, if we're thinking of a system, and this system could be anything, could be a business, could be, a retail company, could be a bank, could be a government, could be a government entity, a department of the government, or it could be any company, a business. Could be a mechanical system like a heating system in a house or a factory. Could be a data set that you want to model and learn from, or it could be some engineering system like an airplane or a robot. So typically this is a control theory. And I think there's not been a lot of distinction in the marketplace. We talk about artificial intelligence. I think that's a very nebulous term, very vague, and I think a lot of people have a lot of different interpretations. I think our view is there's two separate elements to, if you're modeling a system or trying to automate or improve a system. So there'd be system dynamics. This is what governs the dynamical movement of the system from one moment in time to another moment in time, how the system evolves and system evolution. And typically in science and engineering, you would have differential equations. We'd have, Newton's laws, force equals mass times acceleration, really tells us at any moment that, an object that's moving at constant velocity, if you apply a force to it in some direction, then the object will move, it will accelerate and align with the force. And we can solve these dynamical equations and simulate from moment to moment to moment what's going to happen with this system. And similarly, I think I would put LLMs in this category too. It's really done an amazing job in modeling the system dynamics of text sequences, and similarly with other generative AI, like things that generate images and videos. So I think, in the case of an LLM, it's really found a way to model the system dynamics of what's the next word, what's the next token. So it's doing really token generation from the previous tokens and the context that's created by the user input. And so that would be the system dynamic. So it's good at modeling a sequence of words. What you do with that, that's another thing. Similarly, I can model the dynamics of an aircraft and it, have the laws of physics and the Navier-Stokes equations, which are the governing equations that would govern how the forces on an aircraft. And I could simulate if I use these control inputs. So now I have system inputs. The decision-making policy there is another step in that. In the case of an aircraft, there could be a human in the loop. The human is deciding this is what I want to do. I want to turn the aircraft, change the heading into a different direction, want to change the altitude and the speed. These are the system inputs. The real world, the laws of physics will cause the aircraft to move and change its motion. The system inputs have been calibrated with the laws of physics so that the pilot can control the aircraft and get the trajectory going to where he or she wants it to go. There's some measurement capability. The system output is the aircraft changing its heading. There's measurement tools that measure where the aircraft is, what its trajectory is, so that the pilot can adjust their decision and their inputs to achieve the desired outcome. So there's a decision-making policy that wants to achieve a desired outcome. And in that example of an aircraft, it would be a trajectory tracking. So, and in the middle there could be a conversion, the system inputs, in a fighter aircraft, there's a computer that would translate the pilot's inputs into adjusting the flight control surfaces, at 1,000 times a second. Fighter aircraft are very unstable so that they're very maneuverable. And so the computer adjusts the surface controls thousands of times a second, which is beyond human ability. And that translation then, allows the pilot to achieve the desired outputs. So an LLM has the system dynamics. Given an input token that's input by human being, there's some, the system dynamics, a sequence of tokens are created, which Could be natural language, or it could be software program in a certain programming language, or other generative AI could generate video content. That's the output of the system. And in this, there's a human in the loop today. I think there's a human in the loop that says, what is happening? Is that system output what I was looking for? And so there's a human kind of referee, I guess, deciding, is that content wrong or is that right? I think we probably heard from that LLMs can't really a priori determine, is the output correct or incorrect? There's a human expert, which could be just your average user deciding, what am I going to do with this text? Am I going to believe it? I'm going to do something with it. So I think, an AI system or decision-making systems, typically have these two elements, knowing what the dynamics are. In the case, the LLMs have learned the dynamics, but I don't think there's a real formal decision-making AI in there. And I think it's important to separate these two things because, you can machine learn system dynamics. You can learn from data about movement and evolution of systems. From that data, you could potentially model that. I think many systems are too complex to model from data. If you think of the laws of physics, it's not that, Einstein's theory of relativity or quantum mechanics. If we knew the location of every molecule in the universe, I argue, would it be possible to learn Einstein's theory of relativity from that? It's an interesting academic exercise, one that I think people are working on. But I think today there's a human that would design those dynamics. And similarly, in many complex systems like businesses, I think are too complex to, for a system to necessarily learn the dynamics, like in the case of retail that Daisy works in. If you have 100,000 products and you're modeling the halo interactions between products, what is the right combination of products to promote to generate the maximum sales? That's the typical problem that Daisy works on. And if you have 100,000 items and you have to choose 2,000, 100 choose 2,000 is a number that's 10 to the power of greater than 100. So it's more than the number of molecules in the universe. It's beyond the ability of a machine learning system to learn the dynamics in such a situation. So I think having a decision-making policy, this is what we can learn. I think if we model the system dynamics, if a human being creates a set of differential equations like we have in Daisy, we've used a human inventor, invents a set of mathematical equations, differential equations that govern the system dynamics, or the scientist invents the laws of physics. Or in the case of an LLM, you can machine learn the LLM. The dynamics of that system are simple enough that we can learn that. I'm not saying that it was easy to achieve that amazing accomplishment, but that the number of states and the possibilities are finite enough that we can machine learn that. So once you have the system dynamics, then it's what's the optimal decision-making policy. I mean, if you're familiar with the reinforcement learning, it's a lot about finding the optimal policy. So example of a system that would have all of these elements might be a thermostat. A thermostat is a simple system. The system dynamics is thermodynamics. It's a house. We know that if we add heat to an insulated box, your home, that the temperature will go up. We know that if you add cooling and remove heat and blow it outside, you can cool insulated box. And so that's thermodynamics. It's very hard. It's beyond human ability. If you had to constantly be tweaking the thermostat and the fan speed to get to that right level, we have a control system that says the human just puts I want 74 degrees Fahrenheit or whatever, 24 degrees Celsius, and I want to set the fan to auto. Then the system will turn the fan on and turn on the heat or the cooling to move the system to desired temperature. So it's continuously measuring. From the system output is the temperature of the home, and it'll measure that. This is a real-time system, and the decision-making policy could be, if I'm far away from the temperature, turn the temperature on high, turn the fan on high, and heat the system quickly. And as you continue to measure and see the temperature move to the desired target, you would then adjust the fan speed and adjust the heat level that you're applying. And eventually, when you get to the desired temperature, you would turn the system off. And now that's a great system because it's beyond human ability to really maintain a house at a fixed temperature, to stoke a fire or to open the windows or to be adjusting the fan manually is very difficult and time consuming. And the system does that well. That thermostat is a great AI autonomous system that governs the system dynamics. and has a simple decision-making policy. So in Daisy, we learned the decision-making policy. It's independent AI task that's independent of the system dynamics. As I said, we've invented the system dynamics with differential equations that we've simulated. We've done experiments and know that the simulation of retail works with their set of differential equations. And then the question is, what is the optimal decisions that I can make? And the system inputs to Daisy's theory of retail would be, what products am I promoting? What products am I not promoting? What are the prices for all the products at all the stores? How much inventory should I order for each product for each store? That's the set of system inputs. Given the set of inputs, and run them through my system dynamics, I get an output. In this case, we can simulate faster than time and simulate, what's going to happen given this vector decision, promote, not promote, promote, not promote, a flag of 100,000 long, 100,000 prices at each store. If I have 100 stores, and then I have a 100,000 times 100 inventory levels or orders for each product, that put in that vector into my differential equation, and then I simulate what's the revenue. In fact, I put a sequence of decisions. I put this week, next week, for the next year. I can simulate this set of decisions will generate the maximum outcome. My desired output is, maximum sales, maximum profit, maximum transactions, whatever my desired output is. And I can simulate that as fast as and powerful as my computer is. I can simulate a whole year of retail and then find out what is that optimal input vector that gets me the maximum output. And that would be an example of that. And the AI is learning what is the optimal decision-making policy that achieves my desired outcome, right? And so that's an important thing. System dynamics is different than decision-making policy. And I would say the AI, in my mind anyways, in our decision is autonomous. There's no human in the loop in this. Once we've specified the dynamics, the system learns the decision-making policy. It can just run on its own forever and recommend on a weekly basis what are the decisions you should make, optimizing a sequence over a whole year. So if you think of an LLM, what's missing in the conversation, I think, what is the decision-making policy? Today, there's a human in the loop that has to decide, is this good or not? Am I going to believe it or not? Am I going to take action or not? I think there's a separate conversation to say what use cases can we use LLMs for, and what is the decision-making policy that we can infer that achieves a desired outcome. I'm a doctor now. I want to summarize medical research and write a summary of all the new developments in my field, so I can utilize those developments and modify my decision-making process or diagnosis that I make today. And so, we can go read all the medical journals, summarize that output, provide that to the doctor, maybe recommend a new decision tree for diagnosing somebody with some illness. If I'm a specialist in infectious disease, maybe I have a new decision-making tree that comes out of this combination of my existing decision-making policy plus all the latest and greatest medical research. So that might be a great use case. Now, the decision-making policy would be that new tree that is created by this, and the system dynamics. Again, we would simulate. In the case of an LLM, you're reading all the papers. Those are the input tokens that the system needs to go find, and then you're generating a summary using the LLM as the system dynamics, and you're finding back a recommendation, the output that the human then has to review in that case. Similarly, with in insurance, Daisy's looking for fraud and looking at can we automate a claim? So the system dynamics is an outlier dynamic. Is this input to the system an outlier? Is this claim an outlier with respect to with all peer outliers, similar claims, similar times of years for a similar service? Does this claim look normal? Is this a normal looking dental claim for 10-year-old patients? Is that what we normally see? And the system dynamics is really an outlier analysis. How do we effectively identify that as an outlier with respect to peers? Again, we can simulate the effect of multiple decisions. If I have all my claims coming in and I want to decide on a daily or real-time basis, what's the optimal decision-making set against all those claims that maximizes insurance company profitability or customer service or whatever metric you want to operationalize. Again, so the system dynamics is this outlier analysis. We can simulate making different decisions again. So the reinforcement learning finds the optimal decision-making policy against all those claims, pay, not pay, fraud, not fraud in that case, or quoting an underwriting a new policy, a premium based on high risk or low risk. And we can simulate a whole sequence of decisions. We can simulate all the decisions that we've run in the past, or we could simulate the batch that we receive now and decide what decisions can I make to find the optimal outcome. So hopefully that helps. Just wanted to distinguish like system dynamics. How does a system behave? How does it evolve? How does one token affect the next token? That's what an LLM does. And the question is, what's the use case now that I can apply around that system dynamics? And how do I find an optimal decision-making policy that achieves an outcome? And typically, a decision-making policy could be a human in the loop, or it could be no human in the loop. And this is what Daisy does. We have no human in the loop decision-making recommendations that ultimately humans in control and can decide, do I want to listen to the Daisy system or not? Similarly, in an aircraft, a pilot can continue to tweak the trajectory that a plane takes. Yeah, that's it for today. Hopefully that you found that useful. Feel free to follow up with any questions. If you haven't subscribed, follow up on Spotify or our YouTube channel where you'll see this talk and several others, and look forward to any feedback, questions. Would love to respond to those on the next chat. Have a fantastic day.